for I think probably longer than I've known you, and actually we met before we ever worked together.
Well, I was writing programs in serial when I was age 10. It would have been parallel, but the parallel computers didn't exist. A while.
Yeah. So he's basically going to tell you all about the stuff he's doing, parallel file systems in support of people who are doing AI and HPC. So
yeah, thank you very much. So again, this is not formal. Heckle, shout out, ask me questions, whatever you want. It should be interactive. So this is me, or rather this is also me. I did my degree not in computer science, my degree is in civil engineering. I went on and did a PhD in computational mechanics, and then I was a lecturer at the University of Manchester. And my last 3 years at Manchester were supporting the Cray T3E. Have you heard of Cray? I should have. Big computer company, and they're a good employer, and they're based in Bristol. So I don't work for them, but think about where you're going to send your CV. And while I was at Manchester, I got involved in various things. My data science thing, I was a academic researcher doing simulation of ground engineering. And my boss at the time wrote books, and this is the 3rd edition of his book. And anyone want to guess what that is? It's underground, but it's a project I worked on. I'll tell you if you like. I'll give you a clue then. At the end of this little bit here, it goes around in a big loop, big loop, and comes back on the other side. It's the LHC, yeah. It's the LHC at CERN. So where some people do the glamorous stuff to do with finding Higgs bosons and things and colliding things at hugely close to the speed of light, millions of times their normal weight, what I do is dig holes in the ground. So what I did was the computer simulations of digging the holes, and the red bits are the high stress and the blue bits are the low stress. So yes, I worked on CERN, but not the glamorous bit. And then last 18 years I moved out to industry, mostly because it pays more. But I worked first for Quadrix, who were in Bristol. In fact, Quadrix are the company that kind of effectively became, by 2 generations, Cray in Bristol. I then worked with Ken at ClearSpeed. I then worked for Bull, who are a French company, Bull. And then now I work for IBM in the last 5 years. And I've done different roles within HPC. So these days up here, I was doing programming. My old days, I was writing software. Then I moved on to supporting other people. Then I moved on to doing interconnect, GPUs, the systems, and now storage, which are all the different components that make up the technology that you do your data science and HPC on. So that's a typical computer cluster. It's racks and racks of stuff. Some of it all looks the same. Some of it's a bit different color because it's the storage or the interconnect. But really in the HPC system, AI system as well, you probably spend about 60% of your budget on the compute nodes, your GPUs or otherwise, maybe 15% each on your interconnect, which glues it all together, and your storage. And if you don't have good storage, there's no point. You can't do what you're trying to do, because if your storage is too slow or too small, then you can't do data science. You can't do your AI or your gene sequencing if you only have a couple of hard drives to store your stuff on, because you need thousands of terabytes, petabytes of storage typically, and you need big bandwidths, not 1 megabyte a second, you need gigabyte a second of bandwidth. And the same thing with the interconnect. Unless you have a good interconnect, you can't connect all the bits together. You can't feed the stuff fast enough. And the interconnect is probably the biggest barrier to doing all this on Amazon. In Amazon, you have lots of good compute. Storage is not brilliant, but pretty good. What Amazon don't have is a good interconnect. And the other cloud providers don't, because most use cases aren't in HPC, and they don't bother. And so the latency between these different computer nodes is poor in public clouds. And that's why for your big data science type things, whether you're talking about bioinformatics institutes, the Met Office, intelligence services and so on, they all have their own on-premise hardware. And the biggest reason is probably the interconnect, and the second biggest is storage. because only the compute part is the only bit which is easy to buy off Amazon or Google or Microsoft. And the other thing that people forget is running costs. When you build a large system, typically because electricity is so expensive and the building you put stuff in, then you probably cost about the same over maybe 5 years, maybe 3 years, depending on how you look at it. It costs you about the same again just to have that system. And again, there's a lot more to data science and HPC than the compute nodes, which are only about half the total. So here's one I made earlier. This at the time was the second biggest computer in the world. It had 4,000 compute nodes, or 4,000 compute nodes, each one core, and it did 20 teraflops. And that was 10 years ago. Over 10 years ago. That is 20 teraflops. 20 teraflops is nothing nowadays. Your GPU does a lot more than that. Yet you needed a system that big to get 20 teraflops. And if you could do 20 teraflops, you were at the top. You had the second, if not the first, most powerful computer in the world. Yet we're probably close to your mobile phone. Maybe next year, maybe you've already got a phone like this. Maybe your phone can do 20 teraflops. It's a lot. And a teraflop is 1,000 gigas, which is 1,000 megas, which is a million. So it's a million calculations a second is a teraflop. And just before I get onto storage, that's what interconnects look like. That's what I used to do at Quadrix. You have all these computer nodes and they all connect to each other in a complicated mesh topology like a factory. And then at ClearSpeed, we did everything on a chip. And that's a ClearSpeed. I'm sure Ken's shown you a picture like this before.
I haven't, but I have one of those chips on my wall if anyone wants to see it.
And what makes this clever, what makes GPUs clever is rather than having one CPU which does all the instruction decoding, all the work, you have one chip that decodes all the instructions and it feeds it to hundreds, in this case 96, different compute engines inside. So rather than repeat all the logic to do all the program flows and have to have 96 threads in your MPI parallel program, you need one because it feeds, in this case, 96 floating point units that do the calculations. So, I didn't introduce myself properly what I do now. I now work for IBM, doing high performance storage for AI and data science and HPC. The trouble with IBM is that it used to sell laptops. This laptop is a Mac. Yours might be a Dell or a HP. And so IBM is, I think, the second biggest computer company in the world. But apart from that little fact, what do you know about IBM? Tell me one thing about IBM. What does it stand for? Blank looks? It's International Business Machines? Have a stab of how many people work for IBM? And don't say about half of them. How many people work at IBM? Guess? 20,000, more than 20,000 perhaps? And it's about 250,000 people work for IBM, and there's only Amazon have more employees than IBM in computing. IBM in every country of the world, and only Amazon have more employees. But so the second biggest by staff, and turnover is about $80 billion a year business. So it's the biggest IT company you've never heard of. Because IBM's world is not laptops anymore. They sold that business to Lenovo. So Lenovo laptops used to be IBM laptops. IBM are the companies that put in the big computers. So if your university has got a large research computer, it may well have IBM compute nodes in them, might have IBM interconnect in them, might have IBM storage in there. And if you buy something online, it will be an IBM mainframe computer. IBM still make mainframes. IBM's mainframes are still one of the biggest parts of the company, yet you've probably no idea what a mainframe is. But mainframes are those big computers that cost $2 million each, at least, and they do all the transactional processing. All the banks use mainframes because they guarantee that it will never lose data. It does everything 2 or 3 times and checks the answers, a bit like flying moon landings and things. We have multiple computers all doing the same thing, and if any of them fail, the other ones carry on. Those big computers do all the transactions of your bank. Millions of credit card transactions a second and so on. So this is what I'm trying to say. IBM is a big, second biggest computer company after Amazon, but the one you haven't heard of. How long do you think IBM have been going? More than that? It's over 100. IBM have been going over 100 years, and if you think back to where computing was in the early days of electricity, it was all paper tapes and punch cards and things like that. Data processing by doing inventories and punching little holes in bits of cardboard for your storing information, then tabulating those bits of cardboard that had all your records on cards. IBM actually did other things too. IBM used to make cheese slicers. If you go through the records, and so IBM in the UK has probably about 10 offices in the UK, and its research centre, which is a university campus, which is about 8,000 people, I think, work at Hursley, which is near Southampton. IBM have research as well, R&D. They don't just have sales and things. Their R&D in the UK is in Hursley. And there's 8,000 people work there doing blue sky research projects in AI and things that may never come to be products. And you probably, one other thing you might have heard of IBM doing is quantum computing. IBM are kind of one of the top 3 companies doing quantum computing, and we've already got commercial use of quantum computing. And some of that research is done in the UK in Hursley near Southampton. But in that building, or those buildings, it's because it's like a campus. It's a bit like this campus here, really, but just one company. They've got a museum, and in there they've got things going back to the 1920s or earlier from IBM. And yes, I think somewhere in the back distant corner there's a cheese slicer, electronic cheese slicer. So it's one thing. If you remember one thing when you wake up tomorrow morning, is there was a bloke that talked to you yesterday about computers, but he also talked about IBM making cheese slicers. Right, so what I'm really going to talk about is what IBM do in terms of software, and therefore more generally where software fits in. There has been a trend from those days 100 years ago where the balance between hardware and software in IT is shifting, and it continues to shift and continues to shift. And hardware is a long way less important than software. Most things now are software defined. When you design CPUs, if you've heard about FPGAs, it's all software. The hardware is just a vehicle to deliver it on. It's all about software. And in terms of IBM probably makes twice as much money out of software than it does out of hardware. So software is the future, and already is the future. In terms of IBM, we have a bunch of products which do storage, and I'm going to talk about storage. And we give them color codes, and what I'm going to talk about is that one, probably, which is a parallel file system. But it's got the other ones that fit in there. You've got the blue one, which is to do with backing up data and stuff. The red one, which is to do with writing stuff to tape libraries, and a couple others in there too. So if I jump to a picture about AI, those colors come back in again. The green one is parallel file system. It's a big file system that stores billions of files and can access them at hundreds of gigabytes a second. You've got an object store like Amazon S3. You've got an analytical engine that searches all your data to work out what you're going to do AI on, as in which of these are pictures of cats. And then you've got somewhere that stores your data at the end, which is an archive system, because you have an archive system in the mix for 2 reasons. One, you want to make sure your data is readable in 50 years' time. If you write your stuff to some hard disks are not going to exist in 50 years' time. And even your own hard drives, or even SSDs and things you've got yourself, only have a life of about 5 years. So anything you write today to a disk drive or even a flash card is probably unreadable in 5 years, certainly 10 years is unreadable. So IBM and other companies still have a great vision of tape, because tape is you're most likely to be able to read your data in 50 years' time if it's written to tape. You will not read it again if it's written to disk. And I've got hard drives at home, and I've got floppy disks at home and all sorts, which I probably will never read again because I lack the technology to read it. And even if I do have a hard drive, then the connector's changed and the interface has changed. And even USB, you'd like to think it's staying in the same interface, but it keeps changing the plug shape. So things keep evolving, but in terms of tape's where you store data for a long period of time, because you don't get bit rot, as in bit error rate. Random chance of flipping a bit is much lower. And the other reason why you write stuff to tape is it's cheap. About 10 times cheaper than storing it even on some Amazon cloud type place. So tape is still in the picture because it is cheap and lasts forever. But in terms of the AI workflow, this is a typical workflow for deep learning, machine learning. So you have data in at the beginning. You've got to store the data while you're working on it. So we have a file system at the top and an object store, the blue one below it. And you also get fast ingest because you might be doing AI on lightning strikes and things, or data that's immediate coming in, or traffic data that comes in. Then you use software to tag that data, work out what it is, which is a tagging software. That's one of IBM's one. And then you store that. That's just an IBM name for its hardware it stores stuff on. And then you analyze it in your Hadoop. You've probably heard of Hadoop and similar. And then you do your machine learning, and then you go around the loop over and over again until you end up with a trained model, and you get your data out at the end. But it's all iterative, and that's all software defined. I haven't said anything about what hardware it runs on. That might run on power processors, that might run on x86. Some of it might even run under Windows, although in the big data world, nobody uses Windows. But you can if you had to in certain places. So if I just dump back to that picture, so what we're going to talk about is why, for AI and data science, why you need a file system. What benefit does it bring, and what characterizes a parallel file system? So parallel file systems are essential for any big data, high-performance computing, data science, AI. All those are kind of all aspects of the same area of computing. It stores the data that you use on the input, stores the results, and it also stores, very important, the intermediate steps. Because if you run your big analysis on 1,000 compute nodes, then there's for 10 days, you run for 10 days on 1,000 computers, there's a very good chance one of them was going to break. In fact, almost certain one was going to break during those 10 days. So the biggest use case, or the most essential use case, that stops you running on just general purpose systems is that you've got to store the state of your data. So if you're the Met Office, or you're doing a drug design, say, then you run your job for 8 hours, but maybe every 20 minutes, you write out the state of that to storage, and you need to do that very fast because you can't continue the calculations until you've written it out. So you can't spend 20 minutes writing out data that's taken 20 minutes to calculate, because that means your weather forecast won't take 4 hours, it'll take 8. Or won't take 12 hours, it'll take 24. And if your weather forecast is a day late, nobody cares. So if you're the Met Office doing weather modelling, climate modelling, you need the results as fast as possible for the next weather forecast, so people can decide whether to take an umbrella or not. They can decide whether to close motorway bridges because of the wind. They can decide whether aeroplanes are safe to take off and land, and so on. And so you've got to write your data out as fast as possible, maybe every 20 minutes. and read it, and therefore, and if in the next 20 minutes something fails, you have to read it all back again on potentially bringing some new computer nodes into the mix. You also need it to write out the state as you go along for your processing, because you're going to visualize your data. You're going to draw charts of the weather or whatever, or simulate how drugs dock against each other, because in drug simulation you're trying to work out what shape molecule will fit on what shape other molecule to cure cancer or whatever. So you've got to have it because it stores data, not just the input, not just the output, but also the intermediate. It also writes data. Sorry. You can't just write your data into one place. You've got to write it to hundreds of disks or SSDs. So there are three reasons why it's parallel. It's parallel because you write your data across a little bit of your data. If you have a 1 terabyte file, you write maybe 10 megabytes to each of however many disk drives that makes to make it up. You tend to write it in smaller chunks of about maybe 4 megabytes to go, but you wrap around. And you do that because the bandwidth of a single disk hard drive is 100 megabytes a second. But you need to write your file, as I said, the simulation of the weather model for the Met Office, for weather forecasting. The amount of data you've got to write, if you only had one hard drive, 100 megabytes a second, it would take 10 hours, 100 hours to write it out, and that's no good. If you've only got 5 minutes to write the data out, that's why you need lots and lots of disks. You also need to be able to read your data out really quickly. So you need to be able to read your data from many things. In machine learning, you have maybe 100 GPUs which are all reading the data sets to part of their deep learning model. So the same file isn't being read by one computer, it's being read by 100, all at the same time, in parallel, and potentially written back to the same file. So each computer doing its own analysis is writing their own chunk back to the same file. In a climate modelling, you might have one huge file for your results, and each computer node of 1,000 is writing out its own little chunk, because each computer looks after a little area. Like in a global climate model, there might be 10 of those 1,000 computers are doing Western Europe, and other ones are doing little rectangles all over the Earth's surface. So they all have to write all the results together into one file, and potentially read out as well. And also, the reason I showed that diagram of the network, there's no point having a single Ethernet network that just connects all your compute nodes to your storage. You've got to have, if you remember that picture with all the mesh in there, lots of routes through the network. So if a network point fails, it carries on, but also just to get the bandwidth. Because if you have hundreds of disks and 1,000 clients, you can't just have one path between the clients and the disks. You've got to have a mesh, a topology. I don't know if anyone's been here to talk about mesh topologies and factories and things, but you need a network which has multiple paths through the network to connect where the data comes from to where it's going to. And bandwidth. You've got to write it fast, so maybe 25 gigabytes a second. That's probably a minimum nowadays. People now want 50, 100, 200. The biggest computer that at the top of the top 500 needs 2,500 gigabytes a second, or 2,000 million megabytes a second, which is a lot of hard drives. Because a hard drive itself is only 100 megabytes a second, so you need 250 disks just to get 25. And you can't, and if that was only half that number, that time taken to the climate simulation would go up from maybe 5 minutes to dump the data to 10 minutes. And it was even slower, it would take even longer than the compute. And therefore you'd never get your results, or not in time for when you need them. So again, a parallel file system is an example of a distributed file system. A distributed file system is one which is spread out across multiple disks, multiple servers. But they may store, your file may get stored only in one place. So that makes it a distributed file system, so you can have many servers, each with a few disks in, but that doesn't give you reliability, because if that server fails, you've lost part of your data, and it doesn't give you the performance. So you've got to not just write, when you write stuff to Facebook, whatever, what you want to do is not only write the data just to one disk, but to many disks, so you get the performance as well as the protection against one part failing. Examples of parallel file systems, I work for IBM and we've got one, but out there, there's another world out there. Lustre is a popular one. Next slide's about Lustre. Lustre is open source, even though it's been owned by other companies, like Intel used to own Lustre. It's fundamentally open source. Spectrum Scale or GPFS, definitely parallel. But there's others out there as well. Lustre is from RedHat. Ceph is also from RedHat, if you've heard of those. Dell EMC have something called Isilon, NetApp, ZFS, and so on. Oh, one thing I was going to mention about IBM. IBM have just spent, I think, $3 billion buying another company. Do you know which company IBM are buying for $3 billion? Cool. Ken? It's RedHat. RedHat make this one. So IBM have just spent just over $3 billion buying RedHat, the Linux company, and we've already got a parallel file system, and they've got one too. So we're going to end up with another one. Maybe they're different. Maybe this is more small scale. That's big, high end. But yeah, IBM are big enough to buy companies for $3 billion just because they've got some spare cash or something. Now, the reason why IBM bought RedHat is for containers. You've probably heard about Kubernetes and Docker, containerized stuff. What RedHat have technology for is a way of scaling out, orchestrating, running hundreds or thousands of containers, each running their applications in them, called OpenShift. And OpenShift is really valuable, which is why companies like IBM want to buy it, because they can take it to a large market. So this is what parallel file system looks like. This is Lustre. IBM's is the same. You have some management servers in there, and you have some storage things. And here, that's some disks, which look like a shelf, maybe about that big, with some disks in, or SSDs in them, NVMe. And they're usually fronted by a pair of servers. And you have two servers, because if one fails, the other one can do the work of both. Because when you're scaling out, you look at your mean time to failure, or mean time to data loss. And there's no point having a system with 1,000 disks in it if at the point one fails, everything else fails. So you always have multiple servers, and also what we call RAID, where you use 10 disks to store what would normally only take 8, because you have parity, two nodes of parity, or whatever. It doesn't have to be 8+2. There's all sorts possible. Something manages it, and then you have all your clients. Maybe one client, maybe 100,000. This is big data science. So you don't just have one disk, you probably have 500. I said you needed 250 to get that performance figure. So maybe you have 500 of those, maybe not one pair of servers, maybe 10 pairs or 50 pairs of servers serving them. The biggest one IBM's got has got 62 pairs of servers. And when you write one very big file, you'll write a bit of it across all of them. And you've also got your clients down there, and maybe you've got 100,000. Maybe if you're doing some deep learning, machine learning type thing, you want to burst and run that not on 10 computers, but on 1,000 or 100,000. 100,000 cores, effectively. This is big end. So although I'm talking more generally, I work for IBM, so this is about spectrum scale, but different parallel file systems have similar properties. So what spectrum scale is, or GPFS, is a parallel file system, and it stops you having hotspots in the network and gives you the aggregate bandwidth of a large system. So it says there, there's a system there, 400 gigabytes a second. If that's not fast enough, the one that we finished last year in the US is 2.5 terabytes, or 2,500 gigabytes a second or 2.5 million megabytes a second. And you can compare that with what you get out of one hard drive or one flash drive. It's a lot. And you can have caching of your data to speed up your performance. In AI, caching is very important. In machine learning, you're looking at pictures of 10,000 cats, and you're trying to recognize which is a picture of a cat and which isn't a cat because it's a fox, say, or something more useful to mankind than that. But you keep reading the data over and over again. So you have your big store of 10,000 pictures, but often you keep rereading the same files or concentrating down on a subset of those. So in AI, more than maybe HPC, you do read the same file over and over again. In climate modelling, you tend to read your initial data once, do your computer then write out multiple outputs as you step through time simulating it. But in AI, you tend to, it's very heavy on the reads. You read your data, do some neural networks on it, produce a model, feed it back in again, and keep tuning your neural network over and over again. So caching is although AI and HPC are the same, there's probably more data reuse in AI, in machine learning. And also the output of HPC is usually a big thing, like a simulation of every point on the Earth's surface and its temperature and its pressure, for every point on the surface and all the points in the atmosphere above it, billions of data points. Whereas with AI, the output might be, is this picture I give it a picture of a cat or not? Yes or no? So it could be in AI there could be very little end output. It might just be yes or no. Or it might be you've got video surveillance cameras on the London Underground, you're trying to find the known terrorist. All you want to know is, yes, I've seen a terrorist and he's at Bakerloo station or whatever line, just gone on train the Bakerloo line. So in AI, there may not be a vast amount of data as output. It may just be one bit, yes or no. So you need to serve your data in the way you need the data. So a file system is the way you have subdirectories like you have on your own computers, where you keep things in folders and subfolders and so on. But you might also be wanting to serve your data out as objects. So, I don't know if you know what an object store is. An object store is like valet parking of a car. You store your data and you need to know what the URL is, the handle of that to get your data back again. There's no directory structure. So all your pictures you store on Facebook or Google Images and so on effectively is an object store. Object stores are where you only write and read the whole thing. You don't save half a picture on Facebook or Google Photos. You save the whole picture or read back the whole picture. Or if it's a big data file, you only ever read back the whole thing at a time. Whereas a file system, you can edit it and change bits of it, like a spreadsheet or Word document. You can edit bits of it. Whereas an object store is only really has 4 things you can do with it. You can read it, you can write it, you can delete it, or you can scan it, get its information, metadata. And then you've got HDFS. I know you're all very quiet today. Have you heard about HDFS? Hadoop, MapReduce, and so on. So in the big data world, where you trying to create frameworks for data science, data processing, where and again that was written by Facebook as well, processing lots of data. The limitation of HDFS as designed was it's designed to replicate the data. It's tried to puts the data where it's used, and so you typically run HDFS on some 100 computer nodes, each with their own storage, but you have to replicate your data across all of them, or at least some of them. So it's very wasteful of storage, but it's a way of trying to do computing on cheap hardware, cheap cloud-based hardware. Whereas if you're trying to take that sort of analysis and make it run faster, 10 times faster, 100 times faster, 1,000 times faster, you need to take the HDFS model of running your compute where the data is, but expand that to very large stores of data. So then you serve out HDFS from a parallel file system. So a parallel file system has thousands of disks. It serves out that as if it was three-way replicated to your hundreds of computers which are analysing that data using Hadoop, MapReduce, and Swift or whatever. What am I going to say about that there? Oh, you might want to have checksums of your data to check it, whether it's any data loss. Typical error rates in computing are about 1 in 10 to the 15, which sounds a lot, because 10 to the 15 is quite a big number, really. It's like millions of millions, a million and a bit more. But if your data set is a million things of a million things and a bit more, then there's a chance that you'll lose data, that you'll make a mistake in one of your data items. So if you're simulating the weather and you make a mistake, 1 bit out of 10 to the 15 bits gets corrupted, or 1 number out of 10 to the 15 numbers gets corrupted, it could have a knock-on effect. It could make it seem like that a certain point over Bournemouth is now not 20 degrees, but 20,000 degrees, because that's a mistake in the number. And that makes a difference, because in weather simulation, climate simulation, whatever temperature is at the points around that in the next time step is some sort of average or whatever of the numbers there. So if it reaches 20,000 degrees by mistake over Bournemouth, then the next time step, the surrounding cells of the towns around there won't be 20 degrees, they'll be thousands, maybe not 20,000, because so any errors you make in that sort of simulation spread. If you get that sort of mistake in a GPU where you're playing Halo, then you just get a little flash on the screen, and then the next frame it doesn't use that data again, so it doesn't matter. But if you keep reusing, stepping through time, any mistakes that you make get propagated. And that's one reason why you can't just take the GPUs that are cheap in your laptop or your desktop computer and do supercomputing with them, because they're consumer grade and they're there for playing games on, and it doesn't really matter if they make mistakes, as long as they don't make them very often. Whereas in data science, you keep using that data, it propagates. So this is why the high-end stuff, you can't afford a failure of one component because it stops everything, and you can't cope very well with just a random error, because that random error will propagate. If you get 1 point on the Earth's surface that suddenly shows not 20 degrees at 20,000, that will just affect all the numbers that follow on from that. You've also got other things you need in the file system. You might need compression. Your data might compress really well. And if you can compress your data, you can transmit it quicker. And also, it takes less space. So if you're trying to store 1 billion things, but they compress, you can probably store 10 billion things, not just 1 billion. You might want to encrypt your data in medical science. Encryption is a big thing because you might want your patient records might be by law have to be encrypted. And you might want to encrypt your data such that not just one person, it's not your username that gives access, it's where you are. So encryption may be that if you're a data scientist in the medical department, you can sit at a computer up there, log onto your account and read all the files and do your research of your medical data, looking for correlation between eating cornflakes and cancer. But encryption should mean that you can't just go into the university library and log onto your account and access the same data. Because you might want files there, although you can see your own files, there may be certain files or certain directories where you shouldn't be allowed to look at yourself, even though you are the owner of that data, because you're not in a secure environment. And so it's always good, and certainly what we do at IBM, is where encryption isn't just about passwords and protecting your data, it's about where you access the data. So you only access your data from certain places, which of course is this, you know about hacking where millions of passwords get stolen and so on. Well, that's where they do it wrong here, because you shouldn't be allowing, if somebody breaks into your system by guessing a password, they shouldn't get access to billions of things, you should try and lock it down so only certain endpoints have access to encryption keys to access that data. So even though the data is protected itself by a password, you have to be on a particular endpoint, particular computer, to actually read or write that data. It protects you against cryptoviruses too, because if you can write from anywhere, then potentially if you break any one point in the system, you can spread your cryptovirus across all your files. Whereas if you only have certain places that can access certain directories, then it limits the scope. Right, 10 minutes. Just to say, different ways of doing it. Most parallel file systems are like this, where you have storage networks like that previous diagram with storage, disks or SSDs, that's served out, and those are the clients that run on it. Some data science is like this. We have a storage network, that's things from the dark days of the 1990s, like Fibre Channel, iSCSI and things like that, where your storage is connected over a network to the things that actually analyse it, rather than having storage servers that pass the data over a network like Ethernet or InfiniBand to the clients. And that's a Hadoop way of doing it, where you have storages on the compute nodes themselves. But because that might fail, you have to replicate your data. So you might have to have 3 copies of the data, which of course is expensive. And also means that if you're accessing data from there, but the data's here, you have to transfer over maybe a not very powerful network. So I'll probably talk a little bit about this. So when you're doing your data science, your HPC, what you're trying to do is you're trying to take your storage, whatever it is. Your storage might be NVMe, all flash, SSDs, the same technology in your USB sticks and so on your mobile phone. It may be disk. Disk is cheaper. Flash is faster, but disk is cheaper. And also, but disk might go wrong. As in disk you have to protect with RAID, with parity and things in case you lose bits of it. Flash has that inside. Flash also needs parity, but it's inside. Tape's still out there. Tape is still growing as a medium. The amount of data stored in the world by tape still rises every year, even though the number of companies or universities using it is decreasing. The amount of data stored on tape is bigger, because if you think about Amazon or Google Cloud, where are they storing stuff? So although you might be saving your own stuff to Google Photos have to store it somewhere, and that is probably some mix of these 3. The long-term storage will be tape because of it lasts forever and it's cheap. You may want to store it in different ways of storing your RAID, which is kind of similar to this. But what you try to do in a parallel file system like what we do is store all that together into one file system. So you put all that into one file system that contains maybe 100,000 files for 1,000 users, and then serves it out. So imagine your university-wide file system you have here. That's stored off hundreds, if not thousands, of disks and flash and tape and all sorts. But it tries to present it out in one namespace. So in one directory, you might have 1,000 things. You might have 3 things in that directory, one of which is your report you're currently writing for Chem, for your lecture here, and that could be stored on flash because it's rapid access. Your miscellaneous files of your YouTube videos you've downloaded of cats are stored on disk because you look at them 3 times a week. And your downloaded copies of your lecture videos are on tape because you've never bothered looking at them. But if you present all those in one file system, you've got one directory, one subdirectory tree with everything in, and you let the system here decide where to store data. And that's called tiering. Tiering is where you let the storage system have the intelligence to decide what should be on disk or tape or flash. That's the tiering model, which Spectrum Scale can do, and others can do as well. The other thing that Scale can do is it can connect to other things. So it can connect to Amazon S3 or different object stores, so you can tier your stuff out to the cloud. I one of the things I work with, one of my customers I work with is the Met Office in Exeter. I was there last week. They use HPC to process the weather data, and then they seamlessly transfer it to Amazon, because the people that want to use that data aren't a part of the Met Office. They are people that make ice cream, or people that the airport authorities that control whether planes should be allowed to take off and land because of weather, taking account of weather conditions. So there's a data flow in here that you may generate your data on premise, but you might want to export your data to your favourite cloud provider, Amazon, Google, or otherwise. So there's tiering over there. Or indeed, you might have multiple sites. So if you're a research collaboration of universities, this is kind of an American idea, but wherever you happen to be, Bath is part of the regional group of universities, Southampton and Bristol and Cardiff and so on, Exeter. They may want to share data with each other. So you need a data storage platform that can connect to other systems and either read and write your files. As a researcher, you might be able to just go to, you might be working with somebody at Swansea University and they just need to read and write the same data. Or you might want a caching model where if you're over there, you can read your data, but it kind of gets stored locally to save. As you keep rereading the data, it's cached there, but it doesn't store all your data everywhere. It just stores what you've accessed at the site. And then you may want to read your data in all these different ways. POSIX is just a standard way of reading and writing files. Good old NFS, which is a Unix way of mounting remote file systems and reading and writing them. SMB is the Windows way of doing it. Macs use the same thing. File shares, Microsoft servers and so on. What's native? You may be doing HDFS, Hadoop. You may be doing iSCSI, Cinder and Glance, which are kind of block storage type things, where you're running a database, not a file system. So you're kind of accessing your data as blocks, raw blocks. And then you might be doing object stores, Amazon S3 protocol or Swift, which are ways of a put-get interface of just reading and writing whole things, whole files, whole videos, not just parts of them. And then you're accessing them from wherever you're doing it there. Your workstations, your HPC, these are some of these buzzwords out there like MongoDB and Kafka and Spark. Most of the terms up there, apart from these two, didn't exist. Even 10 years ago didn't exist. So data science is a fast-moving topic, and Kafka, MongoDB and Cassandra wouldn't have appeared on this slide maybe 5 years ago because they didn't exist. So what Spectrum Scale and other parallel file systems try to do is separate the physical storage, which can be anything, any vendor, present it as a unified space, but then serve it out to be used by whatever wants to use that data, because these things change so fast. But by having a storage layer that is kind of long term, and even using media which lasts a long time, lets you not having to keep changing things, and otherwise you might have to store the data for your MongoDB in one place, your data for your Hadoop models in another place, and your Spark workloads in another place. It lets you store everything together. And you can write something in by one method and read it out by another. I'm not going to talk about those. You've got encryption and other things at the side. I think I'll skip forward a little bit. I'll show you that one. Skip a little bit. In terms of what I work with, which is called GPFS or Spectrum Scale, it has been around since the early 90s. And it has a history going through there. And the things which kind of you pick up along the time. It started off as being a parallel file system, particularly for multimedia, for streaming video, and still some of the main non-academic customers for these things are your media streaming companies, your Spotify, Amazon Prime and so on, that need to stream media out. That's where it started, and then you have things like tiering, is the ability to have different sorts of media in the system, like tape and disk and flash, and just move stuff around it depending on how recent it's being used. And skipping right to a kind of more modern day stuff, some of these things that were only relatively new, Hadoop's in there somewhere, SMB, Hawk, and so on. Right over there, right. But I'll just come back, final slide. I'll finish off with that one. So this tries to show, bring it back to where I started talking about AI. I know my 1 minute left. Where a parallel file system fits in. It's this big data lake of your data. It connects to other things, and in this kind of workflow, it's trying to suggest you start from a small scale system that might be on some IBM or otherwise servers, just accessing it from workstations, and then you move on to some bigger system where you're trying to train your deep learning, machine learning on a cluster of systems, and you have separated storage at that point. And then you move on to your big production case with lots of servers, a high performance network, and failover systems, login nodes, and that's HPC. Lots of compute nodes, lots of storage, interconnect and management makes it all work together. So those systems are the ones that cost you $10 million because they're big and they're fast. But they all sit on top of the same things. In this case, it's highlighted Red Hat Linux. So the other thing that Linux has made an impact on is that it goes from the smallest size systems through your mid-range systems, if you like, or from the experimental stage to your stabilization of what you're trying to do to your expansion to your production type things. Linux is the overriding thing across there. And down there, we've also got our parallel file system down there too. And it's 5 past, so I'm going to stop.
So, no time for questions, but if anyone's got any.
And if you're trying to work out who you want to work for after you finish, Cray are in Bristol, IBM are in Bristol, as are other vendors, HP sort of in Bristol.
Thank you very much. So that is the last of our guest speakers. It means it is the last lecture for this unit. There is no last surprises. If you have any questions,